Hey guys, welcome to video 34. Today we're going to be using some software that combines the excitement of DCS, Siphon Filter, Legend of Zelda, and Oregon Trail all rolled into one amazing package, and that's PSpice. Now there are other circuit analysis programs out there that are really popular, for example LT-Spice. But I'm going to go with PSpice because I've been using it for decades and it's just a really nice circuit simulator. I'm going old school here. I'm using version 10.5, which is probably 10 or 15 versions behind what's out now, but it gets the job done. Alright, so what we're going to do first here is look at this common emitter amplifier that we analyzed back in video 31 when we looked at AC load lines. We did quite a bit of analysis on this circuit, and we are going to use PSpice to check our analysis results here that I have boxed in red. Now I've also done a few calculations assuming my eta for the transistor is 1.5, and those values are shown in green. Now we're not going to measure little re, but we will measure the voltage gain, and we'll see which approximation PSpice comes closest to. So with that in mind, let's just call up the PSpice schematic editor here, and you'll notice it's a pretty big page, and I'm going to zoom in a bit to make my schematic a little bit larger on the screen. So if I come in 3 levels or so, and I like to start in the upper left hand corner of the screen as well, and start drawing. Here's what we've got: a blank sheet of paper. Normally this page would have a lot of grid marks on it and so on, but I like a clean schematic, so I've turned off things like fancy colors and stuff like that. So we'll get a nice clean schematic, and we're going to start by placing our transistors. So in PSpice we go up here and we click on draw, and we're going to get a new part, and it brings up our parts browser. Okay, and since I know this transistor starts with the letter Q, I'm just going to type Q, and it pulls up all the transistors: 2222, 2N3904. We'll use the 2N3904 here. So I select it and I hit place, and there's a 2N3904. all right, now I'm going to move the labels just to convenient locations, and you'll notice that PSpice leaves some artifacts on the screen here that make the page look messy. What I can do to clean that up is come up to this redraw button, and it'll clean all that stuff up. So there's my transistor. Okay, the next part I want to put on there are my resistors. Okay, so again, up here in part name I'll just type R, and it highlights R, which is the resistor, and we'll place some of these. Okay, so it begins by numbering them R1, R2, R3, R4, and so on. Okay, and it orients them all horizontally. Now I'm going to rotate these vertical to match my schematic here. So what I do is left click and select a part, then I hit Control R, and it rotates it 90 degrees to the left. And I'll do that with all of these resistors. Okay, rotate all of them so that it looks like the schematic that we actually want. And there we go. Alright, now the next thing I'm going to do is wire them up. Okay, I could place more parts, but I'm going to close this parts browser. Okay, and let's connect some of these resistors up. First I'll position them by dragging them to more proportional positions on the page. Okay, and then we'll relabel these resistors. Alright, so R1, I'm going to leave that name, and its value, as we can see over here, is 12K. Alright, I will set that up. R2 is 2.7K. Alright, R3 is my collector resistor, that's 3.9K. And I'm also going to change its name to RC as well, just to match what I have in the schematic. Okay, And lastly, my emitter resistor, its value is 1K, so that's fine, but I'll change its name to RE. All right, then over here is our load resistor. It's 2K ohms in the schematic, so let's change its value to 2K. And I'm going to change its name as well to RL. All right, now again, we've got a lot of artifacts on the screen, so I'm going to clean those up by using this redraw button, and everything looks nice. Okay, so let's next wire these resistors up by using the draw wire button here. Okay, it looks like a pencil with a thin line. So here's what we've got. Let's go from the base over to R1, and then from this node down to R2, and the collector up to RC. Now notice I've got a little bend here. I'll just move that in a second. All right, and likewise the emitter. And finally, let's connect R1 up to RC. Okay, and then we'll drag R sub C over and get rid of that kink in the wire. Drag it down so it looks nice. Okay, you don't need to do this, but I like my schematics to look pretty much the way they're supposed to, and you know, that's just one of my hang-ups here. Okay, so let's again make this nice looking. Redraw, and let's put ground symbols on here. Okay, so we're going to draw, get new part, and I'm going to use an AGND analog ground. That's right here, AGND. I'll place that, and we'll put one here. We'll put one here. We'll put one here on our load, and I know I'm going to need one for my power supply voltage, and I'll need one for my input voltage as well. So I'm just going to throw those down on the page. All right, next thing, let's put our coupling and bypass caps in place. Okay, so part name C. There we go. C is capacitor, so we'll place, and I'll close the window too. So I'll hit place and close. So here's C1. This is our input coupling capacitor. C2 is our output coupling capacitor, and let's rotate this, Control R, and put our bypass cap in place. Okay, so we'll wire these up. Now I could just use the pencil to draw a wire from the base over, but I'm just going to drag this capacitor over, and when it connects, it gives me that exclamation point. Likewise with C2, I'll drag it over till it connects, then I let go and bring it out, and now I'll use my pencil to connect up the emitter, bypass cap, the load resistor, and I need another ground, so let me drag this one over and use it on this cap. Okay, so let's change the values of these capacitors to match our schematic. Okay, C1 over here is 10 microfarads, so 10 UF. Okay, C2 is also 10 microfarads, 10 UF. PSpice interprets U to mean micro, and it ignores F. I just put that there because, you know, it's the correct symbol, the correct unit. Our bypass cap is 47 microfarads UF, and there we go. Let's clean up the schematic, and everything's looking good. Okay, let's pull this over, make that a little nicer looking. All right, let's put in our DC power supply now. That's just going to be a DC voltage source. So I'm going to hit draw, get new part, and it begins with V. So if I type V, I get a bunch of sources, VAC, VDC, and so on. The power supply is a DC source. That's VDC, so I'll place that. And here we go. All right, I'm going to change its name to VCC. And its value for this circuit is 15 volts. So let's change that to 15 volts. Drag this over, and we'll move the ground up, and there we go. Okay, next step, I'm going to put some bubbles here. Okay, now a bubble is just a label like this that says 15 volts or whatever, and every point that's connected to a bubble with the same name is electrically connected together. All right, so B, there it is, bubble, place and close. So here's a bubble, and over here is a bubble. All right, we're going to label that VCC, and likewise this one is labeled VCC. Anything that I connect the bubble to that has VCC as a label will be connected to this battery. All right, now the last thing we need to do is draw our input source, and that's going to be a sinusoidal voltage source. All right, so we hit draw, get new part, and V, and what we want is V, there it is, V sine. Okay, so we're going to place that. This is going to be our sinusoidal input. I'll change its name to V in so it matches our schematic as well. And let's just wire that thing up. Here we go. We need another ground. Okay, so I'm going to come up here, and you'll see this window shows parts that you've used recently. And here is AGND, analog ground. I'll just take it from there instead of opening the parts browser. And here's our schematic. All right, now that's a pretty nice looking schematic, and that's one of the things I like about PSpice. It gives you some pretty decent looking schematics here. All right, the next thing we want to do is set up our analysis. Now we're going to do a transient analysis. That is a time domain analysis of a sinusoidal signal applied to this circuit. Okay, so we come up here, and on analysis we click that, and then we hit setup, and now we can choose what kind of analysis we want to do. I'm going to do, as I said, a transient analysis. All right, and that's going to allow us to specify the time interval we want to examine the circuit. Okay, so our final time, I'm going to use a 1 kilohertz sine wave. So if I want to look at, say, 5 cycles of the input voltage, which gives me a nice looking oscilloscope display, I'll set my final time at 5 milliseconds. And I don't need to change anything else, but the print step is something that just takes up space and time, so I set that equal to my final time. So I'm going to set my print step to 5 milliseconds as well. And the step ceiling tells us the minimum distance it goes between time samples. I like to keep that relatively small so I get a nice smooth oscilloscope display when I look at the waveforms. So I'm going to set that to 10 microseconds, 10 US. U is interpreted as micro by PSpice. And that's all I need to do here. I set up the final time, step ceiling, and print step. That one's not important either. And we'll just hit OK. All right, and then we'll close it. Now, I can't simulate it yet because I have to set up my input voltage source. So I'm going to double click on this V in source, and let's set the parameters. DC 0. We don't need a DC voltage there. AC is for phasor or frequency domain analysis. I usually just set that to 1. We'll look at that in a different video, but for now just set it to 1. Offset voltage, we don't care about an offset voltage on our source, so let's just set that to 0. The amplitude, okay, what voltage do we want this source to be? Let's start out with 10 millivolts, okay? Something that's not going to overdrive the amplifier, so we'll set that to 10 millivolts. 10 millivolts peak, and our frequency is going to be 1 kHz. All right, so we've set our frequency to 1 kilohertz. There, we're all set up. Here's our circuit. It's ready to analyze, and we're going to verify that ICQ should be 2 milliamps, VCE should be 5.2 volts, collector, emitter, and base voltage, and all of the other signal parameters as well. So what we do next after we've set it up is hit analysis and then simulate. All right, now PSpice tells me I have to save this schematic before it'll analyze it, so I'll hit OK, and it's going to save it to a folder I have called PSpice circuits, and we'll call this the CE amp number 1. Okay, CE amp 1, common emitter amp 1. We'll save it. PSpice is now analyzing the circuit, and notice we've got this little icon down here. That's my oscilloscope that runs from PSpice. It's called Probe, and I'm going to bring that up now. All right, so what we can do at this point is add waveforms for our circuit. Okay, I'm going to do that in a second, but let's go back to our schematic, and if I hit the V button up here, since I've done the analysis, this will print all of my node voltages. And here's what we've got. Of course, 15 volts at this node. We've got 7.086 volts at the collector, and our analysis said 7.2, so that's not far off. Our emitter voltage is 2.043. We said it was going to be 2. And the base voltage from PSpice is 2.726, and we estimated that as 2.7. So all of our analysis looks pretty good so far. Let's turn the voltage off and turn on current, and notice here's our collector current. It's flowing down through RC. It's 2.029 milliamps. We estimated it to be 2 mils. So everything's looking really good here. All right, notice our emitter current is just slightly more than our collector current. It's 2.043 versus 2.029, and the difference is we add the base current in with the collector current to get the emitter current. All right, so all the voltages look good. Okay, now if we want to get VCE, it's VC minus VE. All right, we could do that, or we could look at an output file. All right, so if I let's see, analysis, examine output. This is a text file that's a description of this circuit after the analysis. All right, what we've got here is nodes labeled for all the parts in the circuit. We don't need to worry about that. PSpice assigns these alias names to the nodes. Here are our transistor parameters that PSpice used to model the 2N3904. It's saturation current, it's forward beta, noise figure, early voltage, a lot of other stuff, all kinds of things. We're not going to worry about all these parameters, okay? There are way more than we're ever going to need to look at. Here are all my node voltages, operating point information, and here are my transistor currents and voltages at the Q point. All right, my base current, collector current, VBE, VBC, VCE, okay, and PSpice says our VCE is 5.04 volts, okay. Let's just turn this off, and we said it was 5.2, so that's pretty close. All right, now let's get back to the oscilloscope here, and let's look at our output voltage waveform. Okay, so to do that, we'll hit trace, add trace, and let's get rid of these currents. We're looking at voltages. That cleans it up a little bit. And this is why I changed my load resistor to RL, so I could find it easy in this list. And I know that when I rotated RL 90 degrees to the left, it put node 2 up. So I'm going to look at node 2 because that's the one that's not connected to ground. And I'll hit OK. And there's our output voltage waveform. Now notice it is inverted, okay, and that's expected because we put in a positive going sine wave. All right, now we've got a little bit of transient behavior going on here as the circuit settles down to its final values here, okay. We could actually determine this response here using Laplace transforms and things like that, but what we want is the values after it's finally settled, and that's out here somewhere, okay. So notice we had a 10 millivolt signal coming in, and our output is reaching somewhere above 0.8. All right, we can put a cursor on here by clicking the cursor symbol, and I can drag it along the waveform, and you'll notice here that it tells me where my cursor X and Y locations are. There are actually 2 cursors, all right, but we're only looking at one of them, okay. So this top one, it looks like the peak of our waveform has a value of 855.8 millivolts, and that occurs at about 2.7 milliseconds. So with 10 millivolts coming in and reaching 855 millivolts out, we've got a gain of 85.5, and actually it's negative. All right, what did we look for here? We said our gain should be 100 or 65 with eta equals 1.5. So PSpice is telling us the actual gain is somewhere in between here. It's about negative 85. All right, and that's probably closer to what we'd get in a real circuit. Okay, if we actually built this, PSpice does a pretty good job of telling us what we'll really get. So there's our output voltage. Okay, now let me turn off the cursor and let's go down to the next page where we did our load line analysis on this circuit, and that's what we came up with. But finally, what we really wanted to see was what our output compliance was, and PSpice tells us, well, not PSpice, my manual analysis tells me that VO max should be about 2.6 volts and VO min should be negative 5.2. Those are my clipping points. Let's see if PSpice agrees with that. All right, now to do that, what we're going to do is turn our input voltage up so that it drives the amplifier into clipping. So we're going to double click on V in, change its amplitude to say, let's go with 500 millivolts. All right, that should be more than sufficient to drive the amplifier into clipping. And let's see what happens. So we're going to simulate it a second time. Okay, simulate. All right, PSpice is done. Let's add our output trace, which is VRL2. We'll hit OK, and there we go. All right, we see it's severely clipped on both the positive and negative going signals. So let's pull up our cursor and see where clipping is up here at about 2.7 volts, and we said 2.6 VO max. That's pretty good. And our negative clipping is at about negative 4.9. We called for negative 5.2, but you know, that's a pretty good estimate. And actually, if we go all the way over here, it's 5.1, which is a little closer to what we predicted. So the whole point here is to show that all the analysis that we suffered through, you know, and derived for these circuits is actually pretty accurate and valid. And PSpice is indicating that for us. Okay, so this was a quick run through of a PSpice analysis. I know that's, again, a lot to absorb, and I'm going to do another video next that will look at another circuit just to illustrate how PSpice can be used in a practical amplifier analysis situation. So hope you'll stick around for the next one. And again, if you want to download PSpice, it's available online at a number of different universities, websites, and other places. This is an old version. I think I'm using version 10.5, and it's running just fine under Windows 10. So, you know, if you want it, it's out there. Go ahead and get it. I recommend it. It's a great program, and we'll look at some more of this in the next video.